seen earlier zero order and first order, and now we will see the second order type of instruments. We add one more term to the equation for the first order, that is A0 x0 is equal to AI, xi is the zero order instrument. For first order we added one term A1 dxo by dt, and now second order we add one more term A2 d squared xo by dt square. So this is the equation for the second order instrument, general equation. Now we reduce the equation to the standard format, divide everything by A0, say A2 by A0 d squared xo by dt square plus A1 by A0 dxo by dt plus xo is equal to AI by A0 xi. Now we know already this is our sensitivity K, and A1 by A0, and these are new terms. Now we have to define the second order instrument. We have got these terms, this undamped natural frequency of the system, natural frequency is equal to root of A2 by root of A0 by A2, root of A0 by A2, that is the definition for undamped natural frequency. And the next one is damping ratio. Damping ratio recommended by psi, represented by psi, that is A1 divided by twice root of A2 into A0. It is a non-dimensional one. It is a damping ratio. So in terms of these parameters, sensitivity and undamped natural frequency and psi, and d by dt we know already. So d by dt as d, differential operator. We shall rewrite this equation and we get in the following format: d squared over omega n square plus 2 psi d by omega n plus 1 into xo is equal to k times xi. So this is the resulting equation, substituting in terms of omega n, psi and capital D. So this is the differential equation representing the second order instrument. And what is an example in practice? In practice we have a typical example is a force measuring unit, that is a mass. Any force measuring unit or load cell will contain a mass supported by a spring and a damper. So this is the frame, and now this motion can be measured over a scale. Let's say we will say output signal is obtained here, input is Fi, this is your xi signal, xo is the displacement finally we get. So this is a typical second order instrument. Now how to get the equation for this system in the same order? Now consider the force Fi, and part of Fi is used to overcome the or resistance of the spring or in deflecting the spring, and some more part is used to overcome the viscous friction in this damper. The resulting force is used to accelerate the mass. So considering the accelerating force of mass, Fi minus Ks into xo, that is the force used to compress the spring, minus if B is the damping coefficient of the damper, so B into dxo by dt is equal to the force accelerating the mass, so m into d squared xo by dt square. Now this can be brought xo term in one side and Fi input can be taken the other side. So m into d squared xo by dt square plus b dxo by dt plus ks xo is equal to Fi. Now substitute in terms of undamped natural frequency and damping ratio, that is now omega n is equal to root of k by m, and k is equal to 1 by ks, and psi is equal to b by twice root of m into ks. Substitute in this term, then you will get the same, you will get in the same format, that is d squared over omega n squared plus 2 psi d by omega n plus 1 into xo is equal to k times xi is fi. So, in this format we get. So, this is a typical example for a second order instrument. Now, as we have done earlier, we have to find out the first step response and so on. Yeah. For step response, now we substitute as we have done for first order system xs. So, right hand side will be k times xs. So, it is a constant. So, we have to solve this differential equation for xo, and here in this case, depending upon the value of psi is less than 0, psi is equal to 1, psi is greater than 0, greater than 1 is equal to 1, greater than less than 1, equal to 1 and greater than 1. Under these three situations, we have three equations. They are all very long equations, and when they are plotted, we get this following curves, that is the step response for a second order system. So, xo by k by xs, that is equal to 1. This should be the ideal value. 1 is the ideal value. The output value is supposed to correspond to this line 1. It should lie. The curve xo by k by xs should lie there. Instead of it, how it varies. Now, when psi is equal to 0, you get more or less a sinusoidal wave. Psi is increased, you find the oscillation amplitude reduce, and when psi is equal to 1, that is critically damped. One is called critically damped. This is critically damped condition. Under that condition, there is no overshoot. It is just goes smoothly tangential to the number 1 straight line. And later on, you find it's 1.5 and 2 and 3 and all. It will behave. They will behave like that is highly damped systems. They will behave like a first order systems. And the behavior of this for getting the better output, normally people go for psi is equal to 0.7, because 0.7 we find the output will reaches quickly to the near about 1 value without much amplitude, much oscillations. That is important thing. It does not oscillate. 0.7 very small amplitude is there, and later it will die out. And if it is 1, it takes more time to reach reach the ideal value. So, people go for psi is equal to 0.7. Under that 0.7, and also as in the case of first order system 0.95 to reach the 5, this is called 5% settling time, that is 0.95 point. It takes say omega nt is equal to 2.9. Around 2.9 it reaches the 5% settling time. That is time of response equal to 2.9 by omega n. Time of response that is to reach the 5% settling time. For the second order instrument, that we call it time of response 2.9 by omega n. That means higher the omega n, time of response or speed of response is quicker or smaller. 2.9 by omega, higher response will give rise to quicker response. So, that is what you have to learn here. And next we go for the ramp response. Yeah, next is ramp response. Ramp response we know as for first order system, xi is equal to xis dot t, that is velocity at which it varies. That is, this is the way we have seen. This is xi versus time xis. So, it is xis dot. So, xi constantly increase, instead of being a here xs is, this is xs. We have suddenly given xs, the xi is increase suddenly to xs, that is step input. This is a ramp input. That means in this equation xi, now we put xis dot into t and solve this equation as we have done earlier. Again here also we will have three equations depending upon the psi value, damping ratio, that is under damped, critical damped, over damped. These are the three situations, and those three long equations, when they are plotted, you get these curves. Suppose this is here y-axis represents xi and xo by k. The white line represents xi versus time. It constantly increases, and now when psi is equal to 0.2 under damped, we find there is some transient behavior, after which it settles at a certain steady state error. Similarly, for other values 0.5, psi is equal to and 2. See these three. One is I mean under damped, two curves under damped. One is the over damped. For one also it will be something like 2. Between these two values, 1 will be there. Here the steady state error for this ramp input is 2 psi by omega n is analogous to our time constant into xis dot. This is our steady state error. Steady state error for ramp input in a second order system is given by 2 psi by omega n into xis dot, and steady state time lag in the first order instruments is tau. Here it is equivalent is 2 psi by omega n. That is steady state time lag. So for any curve you can find this is our steady state time lag, and this will be the steady state error. This for this curve it is steady state error from the theoretical value. So that is this one is analogous to tau, that is actually our 2 psi by omega n, and this vertical is 2 psi omega n into xis dot. That is for the ramp input. And now sinusoidal input. We know we have to substitute in the differential equation d by I omega. So I omega squared d squared omega n squared plus 2 psi I omega by omega n plus 1 into xo is equal to k times xi. So xo by xi, in terms of I omega is equal to k by d squared over d squared, that is I omega square d squared by omega n squared plus 2 psi I omega by omega n plus 1. It's a complex number. So the magnitude is equal to, I can bring this side, xo by k is plotted. So xo, I can bring xo by k this side by xi mod, that is I omega mod magnitude is equal to 1 by root of 1 minus, we will call beta is equal to omega by omega n, the frequency ratio. So 1 minus beta the whole square plus 2 psi beta plus 1, 2 psi 4 psi square, 4 psi square psi square beta square, 4 psi square beta square plus 1, and phi is equal to 10 minus 1 of 2 psi beta by beta squared minus 1. That is the axis. Now these two equations are plotted here. That is a frequency response second order system. This is omega by omega n is nothing but beta. This is beta value. When beta is equal to 1, it is a resonance conditions. That is, the excited frequency is same as the natural frequency of the system. Then we will we say it is a resonant condition. Under resonant condition, we find if under resonant conditions the amplitude ratio goes to infinity. That is what is indicated here. It goes to infinity and comes back. And when psi is increased from 0, then you will find the maximum amplitude occurs when the omega is equal to omega n. That is what is depicted here. But we find between the between 0.6 and 0.8, say again psi is equal to 0.7,
as you have learnt in the step response, 0.7 is very ideal value. Similarly, here also you will find around 0.7 you have the maximum, that is ideal value, it should be around 1. This should be the ideal condition. So xo by k by xi should be equal to 1. That is perfectly proportional conditions without any error due to the dynamic conditions. So that is achieved when it is size equal to around here also 0.7, in between 0.6 and 0.8. You will have maximum range, somewhat here it will come in between. So the maximum range, so this may be this may correspond, and around it may be around 0.8 up to beta equal to 0.8. You may have the usable range. Hence, for the second order instrument, this is called the bandwidth of the instrument. That is a region in which the instrument is supposed to be used. That is, in this region it is equal to 1. Later on it deviates. Yeah. That's how the frequency response is made use of in fixing the bandwidth of the instrument. Also, when size equal to 0.7, it is noted 0.6 and this is 0.8. That is, the phase difference also is more or less linear. That is acceptable in dynamic response. Higher frequency, this is omega n, that is beta. So at higher frequencies, the phase shift will be proportional to the frequency. So phase shift will be proportional to the frequency. That is also acceptable. It's more or less in this measurement region, it is more or less straight line. So these two things are attained by analyzing the second order instrument. Now we will work out one or two problems in this chapter, dynamic response. First problem 1. There is a balloon rising, in atmospheric conditions. It just rises at a rate of 7 meter per second. That is our speed at which speed of rising of the balloon. This is balloon rises at this speed, and the temperature at it has got a thermometer inside, and also an altimeter. Yeah, thermometer and altimeter and altimeter, which measures the height of the balloon at any instant. The thermometer has got a time constant of 15 seconds. Yeah, thermometer for the thermometer 15 seconds, and the temperature varies at the rate 0.6 degree centigrade per 100 meter. That is atmospheric conditions. The temperature reduces every 100 meter by 0.6 degree centigrade, and the balloon is sending the signals for temperature as well as for the altitude. At when altitude is 3000 meter, there is a signal corresponding to minus 1 degree centigrade. At 3000 meter height, it sends a signal of minus 1 degree centigrade. What is the actual temperature T at 3000 meter? What is the actual at 3000 meter? And also this temperature in what height it is indicated. This is what is done. It is a typical example of a ramp input. It's a ramp response. So we will see how to work out this problem, this ramp response. Now we know that steady state time lag is equal to tau. So when whatever reading we get, that was taken on one time constant earlier. So in the time constant, that is 15 seconds. In 15 seconds earlier, where it was the balloon, that is the temperature. So where it was previously, it is rising at 7 meter per second. So in 15 seconds, 105 meter. So 105 meter below, when it was there, this temperature of minus 1 degree centigrade was shown. So that is equal to height is equal to 3000 minus this earlier this. So it is equal to 2895. When it was at this height, the temperature was shown as minus 1 degree centigrade, but it was shown 15 seconds later as per our theory we have found out earlier. So this is the actual height. But at 3000, what should be the
3000 meter, what should be the temperature? That is steady state error. Steady state error we know already. Steady state error is equal to tau into xi s dot. This is steady state error. In this steady state error, we know tau already 15 seconds given. Xi s dot we have to find out. What is this rate at which temperature is varying? That is, we know it is rising at a speed of 7 meter per second, and the temperature is for 0.6 degrees centigrade for 100 meter. So for 7 meters, whatever be the degree centigrade, that is per second, because 7 meter it rises in a second. So this is equal to that is 4.2 into 10 to the power of minus 2 second. This is the speed per degree. In this that is 1 degree varies degree per second. Per second it varies 0.042 degrees, it varies per second, minus 2 second. 4.2 into 10 to the power of minus 2 second. So the steady state error is equal to 15 into 4.2 into 10 to the power of minus 2. This gives rise to 0.6 degrees centigrades. So as the balloon rises, we have the lower temperature. So at 3000 meter, the temperature is lower by this much. So is equal to minus 1.6 degrees centigrade. This is the temperature at 3000 meter, but it will be shown after 15 seconds. This is the way the ramp system functions. So this is problem 1, and problem 2. A first order problem 2. A first order instrument measures signals with a frequency up to 100 hertz, with an amplitude inaccuracy of 5% error. And these are first order instruments, measures up to signal 100 hertz with 5% error. Then calculate the maximum allowable time constant. What should be the time constant of the instrument? If it has to measure 5% error and up to 100 hertz signal has to be handled, and it is a first order instrument, what should be the time constant of the instrument? For this, we have to use this magnitude ratio equation, that is xo by k by xi is equal to, now for 5% error, it should be, magnitude ratio should be 0.5, that is equal to 1 by root of 1 plus omega square tau square. This amplitude ratio should be 0.95 for 5% error. Magnitude ratio, remaining magnitude should give rise to this much. Omega is known as now 2 pi into 100. 100 is the maximum, 100 hertz signals. Then from this, tau only is unknown, and we can find out tau as 0.523 millisecond. So that's so for measuring with any given inaccuracy, what can be the time constant of the system can be found out by using the amplitude ratio equation. Then another typical example is there. Problem 3. We have a signal xi. Xi is equal to 1 is the magnitude, and sine 0.2t plus 0.3 sine 2t. That is, it is a signal having two components. This is xi versus t. This is one component, and here we have the variation superimposed. It goes like this. So it has two components. Final signal will be, this is the final signal. So one is the smaller velocity 0.2, omega is equal to 0.2 radian per second. Other one is 2 radian per second, that is higher frequency. Higher frequency signal superimposed over here lower frequency, and low frequency signal has got amplitude of 1, and high frequency has got 0.3. 0.3 is the with which the other signal is varying. Suppose this signal is given to two instruments having a time constant, two first order instruments, time constant of tau 1 is equal to tones equal to 2 seconds, and another instrument has got a time constant of 0.02 second. These are the two instruments to which this instrument is given. This is the instrument, instrument. This is given. What will be the this input? What will be the output signal? What will be the output signal? Instrument 1 and instrument 2. Two instruments are there. First you give it first instrument having 2 seconds, and later on 0.02 seconds. Find out the response of this instrument. So we go ahead, that is we have to find out the amplitude ratio and the phase lag. So first take the instrument 1, instrument 1 we take, that is time constant equal to 2 seconds. Time constant equal to 2 seconds. So for this amplitude ratio xo by xi I omega mod is equal to k over omega 1 root of 1 plus omega squared tau square. So here we have the frequency is given 0.2, and the other one 2 frequencies are there. We can take one frequency, that is omega is equal to 0.2 radian per second, 0.2 radian per second, and then we calculate AO by AI, there are XO, this is equal to K by, that is omega is equal to 0.2 we put, and tau is equal to 2 seconds, omega is equal to 0.2, tau is equal to 2 seconds, we will have the ratio 0.93 or this equal to 0.93 K, and phi is equal to 10 minus 1 of 10 minus omega tau, that is equal to minus 21.8 degrees. Similarly, when omega is equal to 2, omega is equal to 2 and again tau is equal to 2, then you will have the same ratio xo by xi I omega, that is magnitude ratio is equal to 0.24 K. So to say, or we can also write this is AO by AI, that is magnitude of amplitude of the output signal and amplitude of the input signal ratios. So now we write the here the phi is equal to 10 minus 1 of this, it gives rise to minus 76 degree. So we have found out both the low frequency high frequency component, the amplitude ratio and the phi, and we write this. Now the output signal xo is equal to 0.93 K into AI. AO is equal to this into AI. AI happens to be 1. AI is 1 for this signal. This is AI into 1, that is sin omega t. Omega t is here 0.2 t, and the phi is minus 21.8 degree. So this is the first term. The second term is now 0.24 K into the AI, that is 0.3 into 0.3 sin 2t minus 76. This is the final equation of the output signal. So now we divide this xo by k, or xo by k. If we divide xo by k, you bring this side, it's equal to 0.93 sin 0.2 t minus 21.8 plus 0.24 into 0.3, 0.072 plus 0.072, that is what is remaining, that is sin 2t minus 76. So this is the equation xo by k. Now this should be equal to xi. If it is not xi, there is error. So what is the error now? See, previously it was amplitude 1 and here it is reduced to 0.93 and the lag is 21.8 degrees. So the slowly varying signal, the amplitude has not reduced much. But what happened to high frequency signal? There it was 0.3 amplitude, but now it has come 0.072. It has almost disappeared. That means
the output signal will be of this nature. So it is following, that is the high frequency component is completely eaten away. This is 21.8 degrees, later it comes, and this one it has reduced to 0.93. That is the first instrument responds only for the low frequency signal, and high frequency signal it produces only small ripples, it is completely eaten away. So if you work out now for the second instrument has got a time constant of 0.02 seconds, that is 100 times smaller time constant. If you work out the same thing for this time constant of 0.02, same steps, then you will get finally the equation xo by k is equal to 1.00 up to second decimal sin 2t minus 0.23 degree plus 0.30 sin 2t minus 2.3 degree. So now you find the original signal is almost there up to second decimal. Here is very small phase lag, and here also amplitude remains same, and the time lag, the phase lag is also very small. So such a signal where there is a high frequency component, we should always go for an instrument having very low time constant. Then only the input signal will be truthfully reproduced in the output side. Otherwise, the higher time constant instruments will eat away the high frequency component. So that is being well demonstrated by this example. Yeah, with this we will close this chapter and we go to the next chapter. We have seen one of the earlier lectures, an instrument inside can be divided into three subdivisions. First is signal input unit, then signal conditioners, and last is signal output unit. Now what we are going to learn here is signal conditioners, that comes in middle of the instrument. That is, it takes the output of the signal input unit and processes the signal so that it can be given to the signal output unit. For example, if signal output is a digital device, then suppose signal from the input unit as analog, necessarily the conditioner should contain a analog to digital conditioner. Or suppose the signal from the signal input unit is a resistance change, for example strain gauge we are using, and then we have to convert that resistance change into a voltage change. That is done normally by a bridge circuit. So bridge circuit becomes part of the signal conditioners. Now the bridge output may be a very small value of voltage and it cannot be given directly to output, so it has to amplify. So next comes amplifier. So like this, bridge circuit, amplifier, analog to digital converters, or digital to analog converters, all these things form part of the signal conditioners. So first we will see the bridge circuit. Bridge circuit necessarily used and often used for converting resistance change into voltage change. We have got both AC and DC bridge. In DC bridge we have only resistances. In AC bridge, resistance, capacitance, inductance, these three passive elements can be combined in any way for each arm. That will be AC bridge, that we will see little later. Now what is the condition of balancing for a Wheatstone bridge? Under balance condition, it is understood EO will be 0. EO will be 0 for balance condition. If it is balanced, then we find the voltage drop across this, if you call A, B, C, D. These are the corners, we name it. So the voltage drop across resistance R1 should be equal to voltage drop across resistance R4. That is, voltage drop across AD, AB or BA should be same as at BA. That means the I1 is the current flow through R1 and I2 is the current flow through R4. Then voltage drop here will be I1 into R1. I1 into R1, that should be equal to I2 into R4 under the balance condition. Then only here we will have EO 0. Similarly, since here it is 0, voltage 0, B and D in the same potential, no current flow can take place in this path. That means this current I1 should go through R2. Whatever it has gone through R1 should go through R2 also. Similarly, I2 which has gone through R4 should go through R3. That means here also I1 into R2 is equal to I2 into R3. Here also voltage drop should be equal, then only you will have the EO as 0. So, under this situation now you find I1 by I2 is equal to R2 by R1 from the first set of equation, and from second set I1 by I2 will be equal to R3 by R2. So, this is called the arms ratio of arms of a Wheatstone bridge for balance condition. We rewrite by using the law of ratios, we can write this ratio in a different way. R1 by R2 is equal to R4. This is I1 into R2 is equal to I2 into R3. Yeah, correct. R2 by R1 is equal to R3 by R2. 3 by R2. Now, this is R2, I1 by I2, R1 by I1, R4. This is R4. So, R1 by R4, we can write R1 by R2 is equal to R4 by R3. This is one way of writing. So, R1 by R2 is equal to R4 by R3. That is the ratio of adjacent terms R1 by R2, that is R1 by R2, these adjacent terms R1 by R2 is equal to R4 by R3. So, again go to the same side, write this equation, or you can write R1 by R4 is equal to R2 by R3, or R4 by R3 is equal to R1 by R2. That is what is R1 by R4 is equal to R2 by R3. Anyway you can write, but what has to remember is the side from where you start. For other ratio you go to the same side. That if we start with R1 by R2, then write R4 by R3, never write R3 by R4. That is the only way to remember it. So, this arms ratio should be satisfied for the balancing conditions. Now, what is the voltage output? What is voltage? That is unbalanced voltage. Unbalanced voltage EO. What is the voltage EO? If there is unbalance in this bridge, then the voltage drop, the difference between voltage drop between AB and AD will be the unbalanced voltage. So, that is equal to EO is equal to EBA minus EDA. Now, what is voltage drop across this? The total voltage E is across the two arms R1 and R2, similarly R3 and R4, the full voltage. So, if you consider only R1 and R2, the R1 by R1 plus R2 will be the portion across R1. Similarly, EDA will be R4 by R4 plus R3, portion of E that will be coming there. So, you find this is equal to E into R1 by R1 plus R2 minus, so E we take it outside, so R4 by R3 plus R4. So, reduce this form, reducing this we have got this equation EO is equal to capital E R1 R3 divided by minus R2 R4 divided by R1 R2 R1 plus R2 into R3 plus R4. Now, the resistances are changed from R1 to delta R1. When the resistances are picking up signals, the resistance changes. So, delta R2 and R3 changes to delta R3 and R4 changes to delta R4, R4 plus delta R4. In such situations, EO will be equal to just E into R1 plus delta R1 into R3 plus delta R3 minus R2 plus delta R2 into R4 plus delta R4 divided by, so R1 plus delta R1 plus R2 plus delta R2 into R3 plus delta R3 plus R4 plus delta R4. Now, it can be reduced because delta R1 is a small quantity, delta R1 into delta R3 will be still smaller,
we can neglect them to be 0. So higher orders of delta terms, and also noting down for balance condition R1 by R2 is equal to R4 by R3, calling it as arms ratio as M. It can be reduced, or neglecting higher order terms, we can reduce this equation into one EO is equal to M by 1 plus M square into E into delta R1 by R1, higher order terms are neglected, minus delta R2 by R2 plus delta R3 by R3 minus delta R4 by R4. To this form, the above equation can be brought down. So this is the final equation. Suppose M is equal to 1, that is the case in mechanical measurements. We are using strain gauges of 120 ohm each, equal arm bridge. So M is equal to 1. In that case, you will find EO is equal to E by 4. M is equal to 1 means 1 by 2 square, that is E by 4. E by 4 into the same term. Yeah. Same term we write it, whatever inside the bracket. So this will be the imbalance voltage of a bridge. We will use this equation to find out the voltage output in different configurations of the bridge. First configuration is quarter bridge. That is, the bridge is not always used with all the 4 arms active. Sometimes one of the 4 arms will be active, sometimes 2 of the 4 arms are active, sometimes all the 4 arms are active. When we give signal to only one of the arms, the other 3 arms are kept constant. That is, R1 alone is varied, and the other 3 will be kept constant. It is called quarter bridge. Only one of the 4 arms is active, others are constant. If it is half bridge, 2 of the arms, 2 of them are active, other 2 will be constant. If it 4 arms means all the 4 will be changed, all the 4 arms will be changed. That is, whenever you give a signal, all the 4 will be changing. So these are the 3 configurations: quarter bridge, half bridge, and full bridge. These are the 3 configurations. Under quarter bridge, what is the voltage output? So that is EO is equal to E by 4 divided where delta R1 alone exists, all the other 3 are zeros because it's a quarter bridge. So into delta R1 by R1. This is simple. In quarter bridge, voltage output is equal to E by 4 delta R1 by R1, relative change of resistance. Now in the off bridge, that is off bridge, what is the voltage output? Now off bridge, we have got 2 configurations. You can have R1 and R2 as active arms, R1 and R2, or R1 and R4, or that is adjacent arms may be made active, or opposite arms may be made active. These are the 2 situations. Take the adjacent arms. Yeah. Adjacent arm is active, off bridge. Now if you want to make adjacent arms are active, and if you want to get any voltage output, then the R1 to R2, they are adjacent arms. Now in that case, the polarity for delta R2 should be negative. If it is negative only, minus and minus will become positive, you will get some voltage. If this one also positive, then it gets nullified and voltage output will be 0. That means adjacent arms for opposite change in resistance. When the resistance changes opposite way in both the adjacent arms, then you can use this bridge. Similarly, off bridge you can use for adjacent arms for opposite change in resistance, and opposite arms, that is 1. I will say 1, 2, and opposite arms for similar change, yeah, or similar change, same change, similar change in resistance. So this is to be observed. if same type of strain, then delta R1 will change and delta R3 will change, both get added up, R2 and R4 being 0, because an off bridge only 2 of them are changing, other 2 are zeros. So following this situation, following this condition, only we have to connect the resistances. If you give similar change to adjacent terms, that is adjacent terms, R1 to adjacent is R2 or R4, any one. For example, we take R2, if you give similar strain, then you find similar strain means they get cancelled out. We don't have any output, but that is what is made use of in temperature compensation. Yeah, that is what is made use of in temperature. That is 3 for temperature compensation. That is for temperature compensation. Similar change is given to adjacent arms. Adjacent arms. Otherwise, for active arms, we should follow these rules. So if we follow these rules, now what is the output? EOS equal to E by 4. That is case 1. Adjacent terms is, this is delta R1, that is delta R1 by R1. We are giving the opposite change, so that is minus delta R2 by R2, and other thing are zeros, so this equal to E by 4. Now if delta R1 is equal to, if delta R1 by R1 is equal to magnitude wise delta R2 by R2 magnitude wise, then we find delta twice, it becomes twice delta R1 by R1. So it's equal to E by 2 into delta R1 by R1. That is, now it is giving twice the voltage output as quarter bridge. That is advantage. Quarter bridge gives E by 4 delta R1 by R1. Half bridge will give you output of E by 2 delta R1 by R1. That is twice the voltage output of the quarter bridge. Similarly, we find in the second case, that is the opposite arms for similar change. Opposite R1 and R3 alone we give. So these things are 0, and also we find delta R1 by R1 magnitude wise, if it is equal, in that case also you will have EOS equal to E by 2 into delta R1 by R1. Yeah, that is delta R2 delta R4 zeros. Now temperature compensations, we have to look into it, probably to